Hi, Preco. This is Limit Applications Day 2. We're going to talk more about that concept of finding what's called a derivative. As a refresher, a derivative represents the slope of a tangent line to a given point on a curve. And just like not every curve is continuous everywhere, right? We talked about with limits, the definition of continuity and how, there's certain points where you might have a jump in the graph or some issue that would cause the graph to be discontinuous. There are definitely points on the graph for certain functions where maybe you can't find the derivative because you can't find the slope of the tangent line. So for this first part, I just want to address really quickly finding certain values where f prime of x would not exist. And the fancy word for not having a derivative is you would say that f of x is non-differentiable at those values. Okay, non-differentiable implying that the derivative doesn't exist. Can't find a slope of a tangent line. So I think it will start to become pretty obvious in these examples here. If we look at the first example where you have y equals, if that's a little faint, it says absolute value of x plus 2. I hope that you can tell that, I can find the slopes of tangent lines at different points except at that point -2. So the issue that we come across for this first example is x equals -2. And the reason why is if you go to draw a tangent line at that sharp point right there, you can say, hey, that line's tangent to the graph. It has a negative slope. This line, that hits the point x equals -2 once. What about a horizontal line? Doesn't that form a line that's tangent to the graph? So there's not one distinct line that would be tangent at that sharp point. And if you want to get fancy, there are calculus teachers and textbooks that would describe that as being a cusp. Okay, so cusps are bad in terms of being able to determine the derivative at that point. Okay, so not a huge deal, but all we know is that f prime of -2 in this case wouldn't exist. All right, moving on to this one over here. What's the issue? I could pick probably a lot of points on this curve. By the way, this is the cube root of x, x to the 1/3, except at x equals 0. That's the issue. And the reason why is you have a vertical tangent line there. Okay, this is the line that's tangent to the graph at x equals 0. What's the problem with the vertical tangent line? The slope of a vertical line is undefined. So we can't find the derivative at that value because it has an undefined slope. All right, so just a couple quick notes as far as that's concerned. And in the last example down here, we have this rational function 1/x minus 3. The only issue that we're going to come across is that this is not continuous at x equals 3. So if it's not continuous at x equals 3, you definitely can't find the derivative at that value. Okay, so we're going to just write a quick note here that it's discontinuous there. The function doesn't even have a value. F of 3 doesn't exist. So if f of 3 doesn't exist, certainly f prime of 3, the slope at that value, will not exist. So there are many other examples probably that we can identify where the graph might be non-differentiable. But here are 3 quick cases. Just know that the derivative does not always exist. All right, moving on to what we're going to get into, which is more of a formal way of defining derivatives, the slope of a tangent line. You can see we have kind of a similar picture to what I set up yesterday. I think we even used the points Q and P. What I'm trying to establish here is I want to figure out what is the slope and then maybe eventually the equation of that tangent line. So what we did yesterday is we picked a point Q that was somewhat close by. And maybe this doesn't look very close right now, but if we connect Q and P and find the secant slope, we can then compare that and maybe estimate the slope of the tangent, right? But we decided Q can get really, really, really close to point P, and that's that limit concept. Okay, as Q approaches P, we're going to get a slope that's closer and closer and closer to the actual slope of this tangent line. So let's see if we can formalize that a little bit more today by defining the points as they're currently stated. You can see that point P has an x value of just a distance x over there. So I'm going to define that as x comma, and the y value that corresponds with that is whatever the y value on this function y equals f of x would be. Okay, so you can list point P as the coordinate x comma f of x. What about point Q up here? Well, point Q could be defined as the x value is x plus some value h. So you can see h is the distance horizontally from P to Q. So the x value of this point is going to be an x plus h. How do I find the y value of point Q? I would plug that into the function. So the y value is whatever f of x plus h is. So we now have a coordinate point to represent both of those. What we're going to do is let's represent the slope in this scenario. So the slope would be change in y over change in x. So I'm going to do f of x plus h minus f of x over the change in the x values, which would just be x plus h minus x. And what you'll notice in the denominator is that those x's cancel out. The x and the negative x are going to go away. So your denominator will actually eventually just become the value h. So what are we trying to accomplish here? We're trying to accomplish moving point Q closer and closer and closer to point P, which we said was the concept of a limit. But I'm going to tell you, instead of it saying the limit as Q approaches P, because I think that gets a little bit confusing in the context of what I wrote down for this slope here, I want you to think about it as what's happening to this horizontal distance as Q gets closer and closer and closer to P. The horizontal distance denoted by h, right? Well, as Q gets closer and closer and closer to P, that horizontal distance is becoming smaller and smaller and smaller. So do you see where I'm headed with this? We're going to take the limit as that horizontal distance h approaches 0. That's what we want to have happen. We want to take the limit as that distance horizontally h approaches 0 for the slope between these 2 points, which we've defined right over here as being f of x plus h minus f of x over h. And this is a super, super, super important concept in the study of calculus. This is called the definition of the derivative. Okay, so this is the most formal way that we can find a derivative by taking the limit as h approaches 0 of f of x plus h minus f of x all over h. By the way, if this looks familiar, we learned this back sometime in September. I should really check the website to see what day it was. And I'm pretty sure in September I said, hang on to this thought, because by the time we get to June, it's coming back again. And here it is. This is called the difference quotient. We did just this part of it back in September. Now that we have a little bit of context of what limits are, if I take the limit as h goes to 0, I hope that that makes sense, that we're going to get the slope of that tangent line. And that's really what the goal is here. Okay, let's put it into practice. And I think once we start to get some practice with this operation right here might actually even seem pretty familiar to you. All right, so in number 1, it says find f prime of x, which we didn't really do yesterday. We focused specifically on the slope at a specific value of x, but we're going to find it in general. And then find the equation of the tangent line at the given point, 2, 6. All right, so for this first one, to get started, I'm just going to write the definition of the derivative at the top so we have it to reference. So it's f of x plus h minus f of x all over h. By the way, as a quick note here, if you plug in 0 for h right away, you get f of x minus f of x on top, which is 0. You plug in 0 for h down here, you get 0. And we know that 0 over 0 is that indeterminate form. We have to somehow, my kids are screaming in the background. Sorry if you can hear that, guys. Sorry. So we have to somehow fix that, right? When we get 0 over 0. All right, let's get started on this first one here. So what we're going to do is this f of x plus h part. We're going to take our function and plug in x plus h for both of those values of x. So it's the limit as h goes to 0 of the quantity x plus h squared plus x plus h. That's just this first piece. You're taking both those x's, replacing them with x plus h. From that, we're going to subtract the function f of x. So subtract this whole thing, x squared plus x. Make sure since you're subtracting a binomial, you put that quantity in parentheses. That would be then all over h. Moving on from there, we are now going to simplify the numerator. Can't plug in 0 for my h's yet. You're definitely going to get 0 over 0 right now. So we have to be able to simplify this. Go ahead and square this. Be very careful doing that. You can't just distribute a square in. You have to either box multiply or FOIL, whatever you need to do. I'm hoping maybe you can even do it in your head to get that. x squared plus 2xh plus h squared. Okay, plus x plus h. And then at the end, distribute that negative to get minus x squared minus x all over h. All right, I'm coming very close to yelling at my own kids, guys. I'm really holding some restraint right here. Okay. All right, so now that I have that on the top, I'm going to cancel things that are in common. We got x squared, we've got negative x squared. We've got x, we've got negative x. And what you should notice is once you've canceled everything, everything left over should have an h in it. Okay, if that's not the case, you have to go back and reevaluate what you did. And this was also true back when we did the difference quotient. So what am I going to do with everything that has an h left over in it? I'm going to factor it out as a GCF. So you should get something that looks like this. When you take out that h as a GCF, why is that a critical step? Because now the h on the top and bottom cancel. And therefore we get that the limit as h goes to 0 of what's left, 2x plus h plus 1. When you go to make a replacement and evaluate this limit, please only plug in 0 for h. Don't plug it in for x. So the limit specifically as h goes to 0. So we get 2x plus 0 plus 1, which is 2x plus 1. I'm going to formalize this by saying that the derivative, f prime of x, is 2x plus 1. Go ahead and try this next part where you find the slope at 2, 6. I'm going to be right back. Guys, it really has to be much quieter. There's too much yelling, okay? All right, I'm done yelling at my kids. Here I am. Okay, so we got the derivative. What do I do next? We want to find the slope at the point 2, 6. Okay, so take the x value from that point, plug it into your equation for the derivative. What does f prime of 2 represents? This is the slope of the tangent line when x equals 2. 2 times 2 plus 1 is 5. So if I have the slope of the tangent line, and I have the coordinates of the point 2, 6, you can go ahead and write your equation. Y minus 6 equals the slope of 5 times x minus 2. This part we should be pretty familiar with from yesterday. Yesterday, we kind of just estimated the slope and then used that slope and the given point to write the equation. But today we're going to do this a little bit more formally by using this definition of derivative. The nice thing about having f prime of x is that you can find the slope of the tangent line at any value of x now. Not just at 2, but you could find the slope of the tangent line at negative 100 if you wanted to, okay? All right, let's go ahead and move across to number 2 there. So we got f of x equals x cubed plus 1. And we're going to find the equation of the tangent line at the point negative 2, 7. Okay, so the first thing we're going to do is use the definition. It's the limit as h goes to 0 of x plus h cubed plus 1 minus the function f of x, x cubed plus 1, all over h. Okay. The hardest part about something like this, but this will come up commonly, I think, in some of the practice, is cubing the quantity x plus h. We already know what it looks like when it's squared, okay? So what do I have to do with that? I have to multiply it by x plus h one more time. So that's going to require some FOIL or some box methods, something like that. I'm just going to write down what the result is because I'm hoping you have the good algebra skills to come up with it. But x plus h cubed winds up being x cubed plus 3x squared h plus 3x h squared and then plus h cubed. So that's the resulting quantity when you cube this binomial. So, oh, I still have kids screaming. That's all right. We're going to get through this lesson, guys. All right, so that's what x plus h cubed looks like. I would almost just memorize it. It's going to make your life a little bit easier. All right, now that I have that, you're going to, don't forget about that plus 1 up here. Distribute the negative to get minus x cubed minus 1, if I could squeeze that in there, all over h. Okay. So now we're at the stage where we can cancel some things. We get x cubed and negative x cubed to go away, 1 and negative 1 to go away. And we're at the point where we're going to take the limit as h goes to 0 of At this point, take the h out of all those remaining terms, which everything has an h, so that's good. So we get 3x squared plus 3xh plus h squared when I take that out as a GCF. Okay. Notice how every single time, it might seem a little tedious, but I write limit as h goes to 0 in front of my work. That is something a calculus teacher definitely would be looking for next year. So if you forget to do it here and there, it's not a huge deal, but this is really the main part of finding the derivative. That limit as h goes to 0 step, a lot of students kind of forget to write that, and I'll tell you, calculus teachers want to see that you're writing that every time, because this is the whole point of what we're doing. Evaluating this limit allows us to find the derivative. If you plug in a 0 for this h and for this h, notice how these terms will both go to 0. So the derivative f prime of x is actually just 3x squared. So that equation right there represents the slope of the tangent line at any given value of x. Well, where did we want to find the slope? We want to find the slope at -2, 7. So we're going to find f prime of -2. This is going to be the slope of the tangent line at x equals -2. -2 squared is 4, times 3 is 12. And then if I plug that in, we get y minus 7 equals 12 times x plus 2. There's the equation of the tangent line at that point.